Welcome to an exploration of cross-impact balances, a powerful systems analytic tool for forecasting complex futures. Cross-impact balances help us understand how multiple variables interact to create self-consistent future scenarios. Let's begin by understanding what cross-impact analysis actually means. Cross-impact analysis is a method for analyzing how different future events and trends influence one another's likelihood of occurring. When event A occurs, it changes the probability of event B, which then affects event D, which influences event C, in a complex web of interactions. This methodology was developed in the 1960s for strategic planning and has evolved significantly since then. The foundation of CIB is the impact matrix that captures cross-influences. An impact matrix is a grid where each cell represents how one variable influences another's probability. Here's a simple three-variable impact matrix C. The diagonal is 0 because a variable doesn't impact it. This matrix shows numerical impacts. +2 means strongly promoting, -1 means inhibiting, and 0 means no direct impact. Impact values typically range from -3 to +3, representing strong inhibition to strong promotion. The key innovation is finding self-consistent scenarios where all impacts balance out. A scenario is a specific combination where each variable is either present or absent, creating a possible future state. Mathematically, a scenario is a vector where each element is either 0 for absent or 1 for present. Here are 4 different scenarios for a system with 4 variables. Each represents a distinct possible future configuration. How do we know if a scenario is self-consistent? Let's explore the mathematical test. For each variable, we sum all the impacts it receives from variables that are active in the scenario. The impact on variable I equals the sum of all cross-impacts from active variables j. If 2 active variables push on a middle variable, one with +2 and one with -1, the net impact is +1. The net impact of +1 suggests the middle variable should probably be active for consistency. A scenario is considered consistent when positive net impacts align with active variables and negative impacts with inactive ones. We quantify consistency with a mathematical score that measures scenario quality. The quality score Q of scenario S equals the sum of absolute impacts times consistency indicators. Delta Y equals 1 when impact and state agree, meaning positive impact with active state or negative impact with inactive state. Green boxes show consistent matches where impact direction agrees with variable state. Red boxes show inconsistencies. Let's work through a concrete example with 3 variables in a climate technology system. Consider 3 variables: widespread renewable energy adoption, implementation of carbon tax, and electric vehicle dominance. Here's our impact matrix. Renewable energy strongly promotes carbon tax and electric vehicles. Each supports the others. Let's test the scenario where all 3 are present. Does this form a consistent future? The impact on renewable energy from the other 2 active variables is +3, strongly positive. Impact on carbon tax is +4, also strongly positive. Impact on electric vehicles is +4, strongly positive as well. Since all impacts are positive and all variables are active, this scenario has high internal consistency. The consistency score is 11, indicating a very coherent future scenario. Now let's examine a different scenario with only partial adoption. What if we have renewable energy and electric vehicles, but no carbon tax is implemented? Renewable energy receives impact +1 from electric vehicles only. Carbon tax receives +4 impact from the active variables, but is not present in this scenario. Electric vehicles receive +3 impact from renewable energy. Here's the problem. Carbon tax has strong positive impact, but is absent, creating an inconsistency. The consistency score drops to only 4 because carbon tax contribution is 0 due to mismatch. This demonstrates how cross-impact balance reveals which scenarios are internally coherent versus contradictory. In practice, we search through many scenarios to find the most consistent ones. With n variables, there are 2 to the power n total possible scenarios, which grows exponentially. For 10 variables, that's over 1,000 scenarios. For 20 variables, over 1 million. This visualization shows the exponentially growing search space as we add more variables to our system. CIB uses optimization algorithms to efficiently search this space and identify scenarios with highest consistency scores. Cross-impact balances are used in diverse fields for strategic foresight. In climate science, CIB maps how different mitigation technologies and policies interact to create feasible decarbonization pathways. Technology forecasters use CIB to understand how emerging technologies like AI, quantum computing, and biotech co-evolve. Technology systems show complex interdependencies, where AI advances enable quantum computing, which accelerates biotech, creating feedback loops. Corporations use CIB for strategic planning, analyzing how market trends, regulations, and technologies combine into distinct future business environments. Despite its power, CIB remains surprisingly underutilized in experimental research. Why? Building impact matrices requires extensive expert judgment, which can be subjective and time-consuming. As systems grow larger, the computational challenge of finding optimal scenarios increases dramatically. Many experimental scientists simply aren't aware that this methodology exists and could enhance their work. There's a cultural gap between traditional linear modeling approaches and the systems thinking mindset required for CIB. Modern extensions add temporal dynamics to track how scenarios evolve over time. Dynamic CIB uses time-varying impact matrices that capture how relationships between variables change as the system evolves. A simple linear model has impacts varying with time. C of t equals initial impacts plus a rate of change times time. Scenarios can transition over time, with the system moving from one consistent state to another as impacts change. The scenario at time t plus 1 depends on the current scenario and current impact relationships. This enables analysis of transition pathways, showing not just end states, but the journey between them. Let's summarize the key insights about cross-impact balances. Cross-impact balances provide a structured way to map complex interdependencies between variables in uncertain futures. Consistency scores help identify which scenarios are internally coherent and self-reinforcing versus contradictory. The methodology has proven valuable across diverse domains, from climate modeling to corporate strategy. Modern software tools are making CIB more accessible, though adoption in experimental sciences remains limited. By embracing systems thinking and cross-impact analysis, we can better navigate the interconnected complexities of future possibilities. The most important insight to remember: the future is not predetermined as a single path, but rather a space of multiple internally consistent scenarios shaped by variable interactions. Cross-impact balances give us systematic tools to explore this scenario space and identify the most coherent futures. Understanding how variables interact and reinforce or inhibit each other is the key to making robust long-term forecasts in complex systems.